Yeah, so it's a pleasure to be here. Thank you for having me, Ken. I'll just go over an overview for today. So just a brief introduction to me, because I do come from a lot of different backgrounds, and that weird starting point sort of is very influential on how I look at some of these common problems that we have in robotics and computer science. Looking at like where we are today in robotics, and then how we can make things a little bit more human-centered. And I thought I'd also end the talk with some resources and references that I find really helpful. This is the more you know section. And then I wanted to save quite a bit of time for open Q&A. So hopefully it's not just like me standing up here, but we can have a bit of a dialogue and a conversation about what's on your mind and what are some things that you guys are thinking through and trying to problem solve or even just problem invent. So yeah, for me, I really come from architecture, the world of design, and I was reaching into robotics. And that background really gives me a lot of forms of different practice to begin to explore robotics and autonomous machines. So in my world, I've been called lots of things. I've been called a designer, a researcher, an artist, an engineer, a scientist. And for the most part, I try to embody all of those and try to navigate the space in between those silos of information. Learning how to speak like an engineer, learning how to speak like an artist is one way of beginning to build bridges from these different forms of practices towards each other. So I do a lot of work in robotics, but I didn't really start there. So I came from robotics through fabrication, so from computer-aided design. A lot of that is really from architecture too. But it's been this constant curiosity, pulling at this thread of how do we communicate better with machines, especially machines that make things. So this first project I want to show you was really one of my first projects where I was learning how to program. So I knew a lot of 3D modeling software from architecture school. I knew how to dream up things and convince people they were worth making real. But I had to skill up really quickly on some technical skills. So programming in particular was one of that. And so this is a project where I'm literally reaching into the computer and 3D modeling, sculpting a form over a 3D scan of my body. And the goal here was to be able to make things that were instantly 3D printable and instantly wearable without having to do any sort of post-processing. So looking at computer-aided design tools and seeing where the commercially available software really breaks down and how we can have a more engaging experience with a fabrication machine like a 3D printer. And then this next project sort of takes that to the next level. So now instead of having a virtual mannequin, you're actually 3D modeling on your own body. So this is focusing more about the interface, more about the interaction. It required a lot more technical skill, which I learned over time, to begin to 3D model a form that could then again be printed and worn back on the body. So Tactim, this was presented at Kai a couple years back, and it's really just a way to begin to think about what the future of our bodies in space are, how we can have computers begin to anticipate and embody what we'd like them to do, and again, piping that communication to a fabrication process like 3D printing. So 3D printers, I've worked a lot with 3D printers, CNC routers, laser cutters, and any machine I could give geometry to and get physical stuff out of. And I was really in a fortunate position to be in a place where they also had industrial robots. So a 3D printer is a 3-axis robot, an industrial arm is a 6-axis robot. And I really started by taking a very normal method of computer-aided design, computer-aided manufacturing, giving that robot geometry and having it do a thing. But because of a lot of this background that I had in making interactive interfaces and connecting interactive geometry to physical output, that I found that for what I wanted to do through these machines had nothing to do with automation, had nothing to do with, there we go, making a thing, but it was really more about the actual interaction. So I really entered the world of robotics through computer-aided manufacturing, but through the lens of interaction just as much. And so these are some of the projects I'm going to show a little bit later, but just to give you, like, this is robot, the rest of the talk is going to be like all robots, but just to give some context as to kind of how I kind of followed my feet into the world of robotics from a completely different discipline. So why don't we just start a little bit about like what is the current state of robotics, what are some of the really hard problems, and what are some of the really tough questions like what is a robot? And for a lot of people, when they think of the world robot, they might actually think of something like this. This is the image they have in their mind, where there are these animatronic demonstrators that are there to entertain you. Or they might think of some pillars of our pop culture and science fiction like C-3PO. Or of course, thanks to the magic of the internet, you might have seen some of these like really amazing demonstrations from advanced research labs all over the globe. But I think that these are kind of a very narrow definition of the word robot. And then on the other side, and when you go ask the general public, like when they think of robot, a lot of the images that they have come from pop culture. And these things, these narratives that we hold dear in the front of our mind about what the future is like are really written from 50, 60 years ago in the past. And yet we're all kind of still inspired by creating that vision of the future from our past. So I like to think of a robot as anything with a mechanical mind and mechanical muscles, and try to keep that definition as broad as possible. And when we kind of open that up, not that those other examples weren't robots, but when we open that up, we can see that there are many species of these machines that are already living amongst us. So industrial robots have been around from the very beginning. So there's robots in our factories and warehouses. There's robots in our cities, streets, and skies. You're likely to bump into one if you visit a hospital. It might be delivering towels or supplies from room to room. You might have one cleaning your apartment right now or entertaining you. And what I find fascinating about this is that the future that we dream about is kind of already here. We have all of these amazing machines amongst us, but we're still kind of fixated on this. This is kind of like our expected vision of the future with machines. When actually, this is like the actual present of the future of machines. And I find this like endlessly more exciting an outcome than we could have never imagined 60 years ago when we were dreaming up the Jetsons. And that's kind of the territory that I like to toil in, is imagining what unexpected outcomes, what unexpected futures we're having with these machines. So there's been a lot of rapid advancements in robotics, especially in machine vision. So object detection, facial recognition, pose detection, localization. These are all things that have made a tremendous amount of progress that have helped robotics advance in a really quick time. These components are making some of those dumb first generation of non-humanoid autonomous machines actually be able to move around in the world. They're helping them see, reason, and get from point A to point B. And these are kind of becoming trivial tasks at this time. There's been lots of advancements in simulation and hardware compensation and sim-to-real transfer. These are things that are not quite commercialized yet, but are really seeing lots of progress in research domains. But there are still some really hard problems in robotics, like manipulation, agile behaviors for under-actuated systems, multi-robot systems, and for me in particular, I think that the social interaction is also a really, really hard problem in robotics that is kind of years away still from seeing some robust solutions. And part of the challenge here is that for these first three, like if you're manipulating something, there is a finite goal state of it was manipulated, it wasn't manipulated. Same thing if you're walking, like you're moving or you're falling over. And for multi-robot systems as well, it gets a little bit more complicated. But for social interaction, there's no finite goal state. It's very ambiguous. Like, what makes a good social interaction? I've met lots of new people today, and I've definitely gaffed a bunch of times that, I would prefer to have not done. But that's just what it means to be human and to interact with people in the world, to negotiate public space together and to negotiate our time together. So this is a very, very messy question. It's a subjective question. And in my opinion, it's a very uncomfortable framing for engineering-based disciplines. What makes a good interaction? But for design, it is kind of like the domain. Design loves these questions with no answers, no finite answers. They're very comfortable. Design as a discipline is very comfortable with qualitative and ambiguous versus engineering, where we tend to like quantitative and solvable. For design, kind of the best part, the outcome that you want to have is a set of best practices versus in engineering domains, you want to have generalizable solutions. And best practices give a lot more flexibility with making bespoke and tailored things rather than having a universal equation for solving the world. In design, avoiding problems is the same as finding solutions. And I think that this is kind of like one of the key secret ingredients for taking a design-oriented approach to some computer science problems versus engineering where, if you found a solution, it means you fixed the problem. And with design, oftentimes the user is a key element of the whole system, that designers try to leverage a person to, again, avoid some of the problems that are in these complex systems. Whereas engineering, in a lot of cases, especially working with industrial robots and in manufacturing settings, that the user is a complication of that system. So I think that this design-based approach is particularly useful for non-humanoid machines, like all of these that we see, this first wave, this first generation of robots leaving the lab to live in the wild with us. Because these machines don't have great ways of talking with us. They don't have these inherent tools for communication. And coming up with clever ways to communicate their intent, communicate what they're about to do, communicate what their task is, and what their internal state of mind is to people that they're sharing public spaces, is kind of critical towards being a good, not really citizen, but a good object person in a shared space. And these concepts are if you've ever taken like a user experience or user interface class, this is one of those fundamental textbooks from Don Norman, Design of Everyday Things. Design is really an act of communication, which means we have a deep understanding with whom the designer is communicating. So if you guys have ever pulled a door open that was a push door, then you've kind of experienced a terrible act of design, right? The objects in our world communicate to us, broadcast to us how we interact with it and how we interface with it. So, you turn a knob, you push a button, you flip a switch. Like the form of it is indicative of how you engage with it. And I think for me, I try to embody a lot of those principles and when I design an interface for a robot. So just to summarize this first section, I sort of see a robot as anything with mechanical muscles and mechanical minds. And with that expanded definition, we can consider a 3D printer robot, maybe even a washing machine or a dishwasher robot, as well as these more normative humanoid robots, bipedal robots, quadrupedal robots, drones, and all these other things. And despite all of the rapid advancements that we're seeing today, there are still things that are really, really hard for robots to do. And some of these hard problems are solvable, and some of them are explorable. In my mind, I think of social interaction with machines as an explorable topic, not necessarily something that can be solved. And then I really feel that design offers a lot of useful strategies for navigating these really messy, ambiguous, open-ended questions that we have with these machines in robotics in particular. But it's really just not yet a part of the the bag of tricks, the tool set that's taught in mechanical engineering and computer science departments. So now I thought I'd take a little bit of time to share a bit more deeply about my work. So these are 3 projects that we'll take a deep dive into. And again, if you have any questions about implementation details, feel free to stop me and we can dig into it. So there are many species of robots, and I'm fascinated by all of them, but for the most part I work with industrial robots. And industrial robots in particular I think are really great being in a place like Pittsburgh where there's this overabundance of decommissioned machines from manufacturing leaving that area. I'm always curious about like what are the next lives of these machines. But beyond that, like these are some of the oldest robots that we have had direct contact with. Since the late 1960s, early 1970s, humans have been working alongside of these machines. And they share a lot of attributes with newer species of robots, newer types of robots that we're just starting to engage with everyday life. So like, if you think of an autonomous car, it's big, fast, it doesn't look like us, very dangerous to be around, and just can do specific tasks in a prescribed way. And a robot has a lot of those same attributes, but it's a less complex system to begin to explore some of these interaction problems and challenges in a safe and controlled manner. I also see that these machines are really kind of pillars of our automation infrastructure, and they've become to symbolize kind of everything that society fears about our future with robots. They act as a symbol of our fear of our own obsolescence. So when people talk about the future of work and the future of automation, they don't tend to think about the smart software that is beginning to automate their job away. They think about this physical thing that they can point at and look to. And I find that really fascinating, and I'll get into a little bit more of that this evening about that. Let's see. But from there is really what I try to do is to find new ways to explore old ideas with these kind of dumb machines. And no one really likes to work with that much because they don't do that much. They just go to where you tell them to do. But for me, I see endless possibilities of sort of taking them out of their prescribed settings, out of their factories, and into new domains. I'm really passionate about inventing better ways to communicate with machines that can make things. For a long time, industrial robots have been the culprit of automation and replacing human labor. Basically, all the easy tasks to automate have been automated. Now what we're working on is using these tools to enhance or augment human labor. And that to me is very exciting. Industrial robots are really fantastic CNC machines. You put a different tool at the end of the arm, and all of a sudden they can do a whole different thing. So in the morning you can be doing spot welding, in the evening you can be doing painting. It's just highly adaptable. Another thing that I'm working towards is finding ways to bring these machines out of factories and into live environments. So onto construction sites or onto film sets. There's chance for unpredictable objects like people to be moving into the environment. That's one of the reasons why I wanted to build the system, to give this robot eyes so that it could actually see me and we could safely collaborate in a shared space. If I'm wearing or if I'm holding these motion capture markers, it knows where I am in space, it knows how I'm moving in space. Now all of a sudden we can give the machine a nuanced understanding of our intention in that space. You can get someone who's never seen a robot before and have them begin to do creative things with just a couple minutes of interacting with the machine. Yeah.
I was watching last night a video about these guys climbing up a waterfall, and they had drones watching them, and it was like terrifying watching them because they were like hanging off of this cliff. But I feel the same way with this because that is so that could wipe you out in like a split second. How do you manage that whole safety aspect?
Yeah, so this is actually part of an artist residency with a company, Autodesk. They're over in Pier 9 in San Francisco. And for them, they invited a bunch of artists to come in and do things that their engineers couldn't imagine with the machines that they had there. And so, of course, we're always putting life and limb at risk for that. But it was interesting. So there are some safety measures in place here. For example, it's running in manual mode, which limits the speed. I'm holding, it's an unfortunate name, but a dead man switch, which means if I press too hard or let go because I get knocked out or something, that the motors disengage. But it was interesting to work with a health and safety professional at some corporate 9-to-5 job who's like, you want to do what with a robot? So I had to go through a risk assessment, which is basically just a spreadsheet that has all the things that can go wrong to you and hurt you. And you start off and the columns are red, and you got to get the columns to green. So like, one of the things we had to discuss is how am I going to mitigate my chance of decapitation? And so an engineering solution might be like, oh, I'm going to make robust software and do automated testing. And the design solution is I'm just going to operate it below my head, and then I can't possibly get decapitated. So it was really interesting. So this is very much like a closed course professional driver scenario, but this kind of risk that you talk about and this feeling is something that I didn't really expect out of the project. I was really doing something pragmatic from the start, which Autodesk had this robot that was just sitting there doing nothing, and it can move around in the world. And they also had this camera system, this like really expensive motion capture system that couldn't move, but it could see the world. And I just thought, well, why don't we just put the two and two together? And so that's really where this project came out of. But what happened was that because of that video and the storytelling behind it, a lot of people saw that, and for me, you know, I had this effect on the robot where it was going where I was telling it to go and to do what I was telling it to do. What I didn't expect is that that robot had an effect on me, that now all of a sudden, just from the fact of how it moved, that I sort of felt kind of like this bond with it, that I could anticipate it, that we were kind of in a little bit of a dance here, anticipating each other and moving around. And as I was developing the software, you know, more and more hours in front of this robot, I began to feel less and less like a roboticist and more like this. You know, like I was like this animal tamer in front of this big beast of a machine that was so excited to follow me along the lab and hopefully wouldn't crush me. So what was interesting is that other people saw this kind of relationship too, which was, again, like not the intention of the project. It was a very pragmatic thing. I was actually doing some follow-up research from the 3D modeling on the body. I wanted to 3D print on the body. And so I had built a handheld extruder, and I just wanted to put it on the robot, but I needed some software to make sure it was safe to do that. And this video kind of went out into the internet and took on a life of its own. And so lo and behold, I got a call from a curator asking, you know, we're doing this exhibition about fear and love, and automation is one of our topics. And, you know, can you, I see this relationship that you have with this machine, and can you replicate that for a crowd of people so we can start to grapple with some of the anxieties about what our future is like with these machines? And I said, yeah, sure, no problem. It's easy, you know, one person lab code for 4 weeks to transfer to a 6-month installation on a different continent. No problem. Also, there was only 4 months until the opening as well. So yeah, no problem. And then I hung up and freaked out and tried to call all the resources I could to figure out how to get this thing done after saying yes to it. So always say yes and then cry and then you figure it out. That's the moral story here. But this ask from the curator, it kind of reminded me of, you know, Victorian era zoos where people would bring these exotic creatures into these confined settings for the spectacle and entertainment of the masses. And so I decided to really play that up and to bring an industrial robot to live in the Design Museum London for 6 months. This is Mimas here. You can see this is, so again, when I design an installation, it's not just the interface with the robot, but it's the space around it. So thinking about what sensor placement is, as well as the enclosure and what that actually looks like. But why don't I just introduce you to her here? So this is, the museum also was doing a grand opening. It had just gone over like a £1 million renovation. And so they were physically like putting the building together as we were installing the system. But here she is. And so there's a lot of differences here. So you see there's no motion capture anymore. It's tracking a crowd of people. And one of the challenges was like, how does a single robot with a single body and a single face begin to engage a crowd and feel connected to a crowd and not pay too much attention to one person, not pay too little attention to some people, and sort of strike that balance. So this is a little bit of the system that I developed. It is, again, just we're doing crowd tracking using a bunch of Microsoft Kinects. So the Kinect V1 is really a fantastic sensor. I have like a doomsday horde of it now that it's end of life. I have like 23 of them shared and a computer that I don't update for fear of driver failure. But by mounting those around the enclosure, I could give Mimas a bird's eye view of all the people around her. So this is a peek into the motion tracking system. All of these people are blobs here, and we can extrapolate some hard numbers and begin to infer some different relationships with that. So for example, for people who have been at the exhibition for a long time, and they're getting closer and closer and closer to the robot, then maybe there's a bit of trust that has built up, and maybe Mimas should begin to favor that person when she's deciding which person to see next, when her attention span runs out for the current person that she's looking at. Similarly, like we know if there's short people and they're moving around, that maybe those are kids. And like, well, a great way to get people into an installation is to have kids run around more. So maybe she should go favor kids even more. So that's just sort of the ways to begin to draw these soft, fuzzy ties from hard numbers to actual experience. The next challenge for me was really thinking about like, well, if Mimas, if this industrial robot is an animal that was born from a factory, how would it actually communicate with the things around it? And for me, I was thinking about just its body language. So I really tried to restrain the palette here and not put a face on the robot, not put a screen on the robot, but just really push the limits of what motors, posture, and motion could actually communicate and connect with people. So there's a little bit of sound engineering here even, like for certain things, for example, I could engage, if a person was in a certain position, the fifth motor would engage, but it has a much higher pitch than the base motor. And for that, it seemed like it had a chirp and a jerky movement to match with it to get that sound. So all of those things were thought of in a very restrained way, but to a very deep level to begin to make these more emotional connections with people. And kind of with those few simple ingredients, just her posture, her motion, and the sound of her motors, you can really begin to breathe life into a piece of manufacturing equipment. So I think part of the strange appeal of this installation is how something that is so alien to our own biology can still seem so lifelike and so connected to us in some odd way. And what I see this machine as doing is showing us reflections of our own humanity. So when we see Mimas give us a gentle nod or a curious little sniff, we're really seeing part of our own emotions, anxieties, and curiosities, bits and pieces of our own human condition projected onto her and reflected back to us. And when you're able to look at a machine and it looks back at you, you start to lay a foundation for communication and understanding. So there's a lot of things that are playing to my favor here. So for example, in this installation, I try to leave some breadcrumbs behind for how the technology is working. But still, so we tore out the connects and put them in these really nice aluminum enclosures. It is a design museum after all. I was making software, was my gift to that museum, but I still wanted some tangible, beautiful object to be in there. So there's these really nice things in the ceiling for it with the depth sensor looking down. But people still think that the robot is looking at you through its face. And that bolt pattern, which isn't even, it's a 6 pattern bolt pattern, but we can't help but start to see that as eyes and the snout and this face and mouth looking at us. And it was really interesting to see kind of the range of emotions that Mimas would elicit. And social media was really great for this. So when you do a user study in a lab, you might get 10, 15 people into the lab to begin to try out your system and to give some feedback on it. When you release something in a museum, there's 100,000 people over 6 months that are seeing it, and a good number of them give you some feedback online about what they would do with the robot, and some of them were quite lewd. And these are some of the more important ones, right? Which is people grappling with why this robot felt kind of creepy and yet they still enjoyed it. Or that if we're totally creeped out and didn't like it at all. And at least for this installation, I really wanted to not have a particular voice, a particular opinion on what people should think about our future with automation, but just begin to have an opportunity for them to contemplate what those consequences are and how they feel about that. So Mimas was a project that explored what it was like for one robot to be surrounded by many people. And I was fortunate enough to have an opportunity last year to make an installation that looked at many robots surrounded by many people. So this installation, Manus, was commissioned by the World Economic Forum with their Global Fourth Industrial Revolution program to really help policymakers think about what our future with these machines are. And to give them kind of a snippet of a future when intelligent autonomous machines are everywhere in manufacturing and potentially in our environments. So Manus is this follow-up project, and it's a set of 10 industrial robots that are programmed to behave like a pack of animals. And again, the physical design is a big part of this. So they're in an assembly line. There's little hints to show you that things are wrong. The robots are actually really, really close together, so they can hit each other. The work surface that they're on is actually a bed of light, so you wouldn't actually use that. And the enclosure itself is kind of tight. We used a reflective material to sort of amplify the number of robots that you would presumably see in those reflections. This is a little bit about how the system works. So this is 10 ABB IRB 1200 robots. They have each have a control box that shoves over here. We had to add last minute vents because it overheated in this enclosure. And then there's one central PC that is the mastermind, sort of connecting all of these robots together and driving the kinematics and motion generation for it. But when you add all these layers of engineering together, you get kind of these really special moments where these behaviors sort of ripple through. So each robot moves individually, but they are all aware of one another. And the kind of sensory connection made by this connected system gets these intertwined behaviors that ripple back and forth when people walk by. And so the robots in Manus, these are using the same exact sensors as the big robot Mimas in London, but they're quite nearsighted. So that was another way to get people to come close and feel extra surrounded by these machines. And they don't have a bird's eye view, they have a worm's eye view of the world around them. So people still think that the sensors are coming from the snout, but it's actually coming through the feet. So the sensors are embedded in the base and are pointed up at the people passing by. And with that, you can get some of these rudimentary hallmarks of human gesture. So head position, hand position, how close you are, if you're leaning in with your head, if you're moving back with your head. And those can go to the kinematic system that then begins to generate these different motions. So the motion simulation here, I like to use a lot to start with things that replicate or simulate natural movement. So I'll start with a flock algorithm or a Boyd algorithm or some sort of agent-based algorithm, and then I'll tweak and tune it based on a bunch of different parameters to get the kind of motion that I like that renders really well on a machine. And then there's the same kind of logic where sometimes if you're too far away, that some of the robots just won't care and will ignore you, and or we'll go look at someone else. So there's body tracking in here, there's simulation, there's motion generation, but when you embody those systems into a physical entity in a physical space, you get these really powerful moments that occur when something goes from an expectation of control to an expectation of connection with these machines. When I work with machines like this, I'm always trying to tease out some of the poetic experiences from these very pragmatic technologies. I often approach it from a pragmatic starting point. How can I solve this problem? And get a robot moving as quickly as possible and see kind of what experiences emerge from it. But at the core of these installations, really, I feel that if robots are to share our cities and streets and skies with us, that they need to be more than useful. They have to be better than just the tasks that they complete. They need to add meaning into our everyday lives. This was a really unique opportunity for me to begin to make something that was for policymakers. So it wasn't in a lab or research context, it wasn't in a cultural context in a museum. It was really in front of people who are responsible for deciding what our future with these machines are. And I wanted to show them that we have a choice in how we engage this tech, and that the future is not a foregone conclusion for how these machines behave. And we also have a choice in how not to use this technology. And so it's a really, really exciting opportunity to begin to engage the policy sphere with this installation. I've since gone on to become a council member on one of these boards, and that's a very new experience to me. It's another, like, when I went from design into computer science and interaction, I felt like I had to learn a new language, and this is another new language I'm having to discover and learn and fumble through and gaff through. But it's a pretty exciting challenge.
When you do the simulation, do you, because you have to tune a lot of dynamics parameters in here, damping and just the accelerations. I mean, what's your process of doing that? Is it
So we're not
tuning by trial and error, or do you do it systematically?
a lot of it is the real process is make something that moves as quick as possible and get other people other than me in front of it. And then I turn into David Attenborough and I just observe what happens. And unlike him, I can go back into the brain and tweak things on the fly to change the behaviors and see how it happens. So it's a very iterative process, and I think that's something that, for me, could be worked into more of a training scenario where I'm giving expert data as a starting point that then begins to fold into a smarter way of being to tune those parameters.
But, I mean, you have the simulation, so you don't need people at this stage, right?
These are, I'm not simulating the person, but that's some cam data of someone walking around.
Oh, I see. So you just get some candidate, and then you see how the whole thing interacts, and then you start tweaking, so you can replay what that would have been like under all kinds of different conditions. And it's just like a huge amount of experimentation and trial and error, right?
Yes, and that's one of the benefits of having a restrained palette in what these robots are doing. Like, if I had to also change the colors of the LEDs at the table, or if I also had to have the robot do a specific task at a certain time, that all of those things would let me not hyper-focus on just what the motion is communicating and connecting with the person.
I mean, we have some sense of how hard it is to program a robot to do something. You do everything in joint space, I presume, because you don't do it with singularities.
Exactly.
What's the mean time between failure on this?
What do you mean?
When you get it going, how often does it fail?
I never fail. No. No, so for this, it's challenging, right? So if we look at for this was a 4-day event in China that, again, the request came about 8 weeks before the actual demo. So it's like, yeah, no problem.
You put this whole thing together in 8 weeks?
Yeah.
Oh my God.
A lot of it was code that was ripped out from the previous one that I thought was reusable, and then I ended up rewriting, and it was a lot better and a lot faster that way. So this was, for those 4 days, I was standing by it, and I had another person standing by it to answer questions and to make sure that there was no issues. But one of the things that didn't work out is, if you look at let me go back to the plans here. So my goal for this, what I really wanted to do was not just have the robots look at you, but if you tapped on the glass, the robots would tap back in that place. And that was a big idea for why I had the sensors in the bottom, was because they were detecting that plane that you could then use as a touch sensor. So it's the same technique that I used on 3D modeling on the arm, but now I could just use it on the surface. But that kind of got it scoped out because of the time constraints on the project. So that's kind of the process with this, is ambitious goal, not enough time, not enough resources, that gets tailored down to a very a polished project more than a technically challenging and edge pushing for things like this. When you're in the lab and you're shooting a video, that's really when you pull out all the stops and you can try 6 or 7 times to get something just the way that you want it. But when it's in a live setting, it's a lot less forgiving. Which is to say that for this system, so I had 2 robots in Pittsburgh that ABB lent me, and I was assuming that when I got to the other side of the planet, that whatever I developed would work on 10, and it was a little bit of a, back of the napkin calculations and fingers crossing that presumption would hold true. But I had 2 weeks to install on site, which let me install and fine tune and do a little bit more programming and gain a little bit more time back. But for things like this, I was really grateful to be able to be next to it. So I would have, if this were something that was to be to travel without me next to it, I would have tempered back a lot of the feature set of it, which is what I did for Mimas as well. So this installation needed to work on a different continent for 6 months, and it was being operated by basically like undergraduate art students that worked at the museum. So it really had to be baby proof. I mean, we literally had to baby proof this installation. For ISO safety guidelines, you're allowed to have about 8 inches from the ground of the machine. There can be a gap there, and because that's a factory setting, I think that's a very reasonable regulation for that. But when you take this into a public setting, you have no idea if a child is going to just crawl under there and go into there, which can be very, very dangerous. So I had to tell ABB that no, we can't follow those guidelines. We have to be stricter than those guidelines in order for me to sleep at night. And I did have a lot of sleepless nights. This installation in 4 months was down for 4 days, and it was not my fault. They needed to replace the sensors in the ceiling was powered. They needed to be power cycled every day because they're Connect V1s and they're not designed to run for 6 months nonstop. And they just needed to change the batteries in the controller, the remote controller, to turn off the power. So that's why I was down for 4 days. But I feel like there's a responsibility for your interactive things that go out into the world to work, especially for museums, because it not only reflects badly on you, it reflects badly on the museum, and also you might be ruining it for the next person who wants to make an ambitious interactive project that they're not going to trust that it'll work then.
So I would say thank you for doing that, because I have to say I've been to so many exhibits where there's like closed, broken,
Yeah.
and it's just sort of, I think it's why a lot of museums shy away from doing showing this kind of work. And a lot of people don't take that kind of care.
Yeah, it's hard because like you want to push the envelope so hard, but at some point you have to say that the professionalism and the experience of it matters more than it being broken.
Well, most of my students know, how hard it is to get somebody to work to take a video for a conference. But there's this common perception. Well, art is a lot easier than engineering. Engineering is really hard. But trying to put together a show like this and let it run unaccompanied for like a day, a week, a month, there's nothing comparison. Right? Nothing that we do in a lab is comparison to the difficulty of getting something like this to be that reliable.
I think another aspect that I haven't really been able to capitalize on is the fact that you just get so many more people coming through your system to experience and use your system than doing a user study at the end, especially for interaction-based things.
Do you actually capture data that you can use for that?
No, it was a little skeeved out. I was a little skeeved out. No, fortunately for my PhD, I was allowed to use the exhibition record as publication, which was convenient. But yeah, it's something that it wasn't thought out ahead of time, and so to keep the data and collect the data, I didn't think was right. But integrating some sort of structured feedback that would be useful for the research community, I think, is something that is missing, and that could be really, really useful. Because again, you just get 100x, 1,000x times the people that come through.
Yeah, it's data. Okay, great, Madeline. Thank you so much. I have to watch the clock because we have another meeting, and you have to go get ready for your meeting.
Yes.
So thank you very much. All right, you can, if you want to ask her a couple questions, I think there's someone coming over to get her very shortly to take her over to the art museum.
Yeah, I'm happy to chat until I'm pulled away.
Okay. Do they have phone number for you and vice versa?
Pardon?
Just make sure that you're reachable.
I believe so, yes.
Okay. There is a little challenge here because of the we're in a basement, so phone may not be great. Do you have some bars?
3 bars.
Okay.
I think I should be good.
Great. Thank you. That was fantastic.
See what you're saying?
Yeah, really good. I'll be there at 6:30 on the dot.
No worries.
I'll be rushing over from you. All right, I'm going to go over to the other.
Like, how many Kinect sensors are inside this exhibit?
This one there's 5 in the front, 5 in the back, and 2 on the sides. So what ended up happening is that, as Ken said, I had to change the scope a little bit. So originally the idea was that they would begin to do backflips and look behind them at people and then come back and forth. And kinematically that worked, but I didn't bring enough cables for the ones in the back. So it's like one of those things that for a 4-day event, and trying to source that in a different country was really, really challenging. So I worked so hard on getting the kinematics right for it to do a backflip without colliding with its neighbors, to look at people behind, and then I didn't pack the cables. It was immensely disappointing. So they're all running on one PC with there's 4 PCIe USB slots there. So there's up to 16 is what I've done on a single PC.
So like it's just like a glass like installation like in the middle of like a walkway or something? Or?
Pardon?
So is it like in the middle of a walkway or like what is it?
For this installation? Yeah, so that also had to do a lot with the form of it, is that it was between 2 escalators coming up to a top floor, that people would walk by it kind of on angle. So you wouldn't approach it straight on, which is why I kind of wanted to have this like double take little gesture that they would do when a single person would walk by. So you weren't sure if they're actually looking at you. And then when you turn around, they sort of go back to normal.
It looks like it's on a bridge, and it's like on like the end of the bridge, so like when so like I was like wondering is there like another side?
Yeah, it's on a balcony, and it's positioned far enough away to have people walk by, but because the back sensors weren't working, we sort of, that became our back of house area a little bit. Yes?
For this one, like, are they all reacting to just the Kinect, like, sensor data, or are they, like, perceiving it like they're, like, in the neighboring robots?
Yes and no. So every robot, because it depends on what you define as perceiving, right? Because these machines can have their brains outside of their bodies. That the software that's actually running on the robot controller is really, really dumb. It's just, a socket connection, waiting for a position command, a joint command, and then a couple special edge cases for that. So the master computer is really controlling everything there. So the master computer knows what everything is doing, but the physical body presence of it, that's actually on the control box, they think that they're all the world coordinates, basically, for that. So for industrial robots like this, you can connect them to, it's a really problematic term, but have master-slave relationships. But that's really for a very precise use. It's usually for coordinating and synchronizing when two things are going to touch something or act on a single material. And for me, that was not, it didn't offer enough control over what I wanted to do. But good question. So now you know all my secrets. Buy a lot of V1 Connects, always say yes, and then figure it out after. So are you guys, what sort of backgrounds do you guys come from? Is it computer science, mechanical engineering, robotics, art?
I know like half of us started Ken's lab from computer science.
Computer science? Mm-hmm. Anyone focusing on controls?
Well, I started on mechanical,
Uh-huh.
and then I ended up making mechanical engineers.
Mm-hmm.
I don't know, it's like a bit more on the hardware side.
Yeah. That's the hard part. Programming them is the easy part. The hardware is.
I like the opposite.
Oh man.
Hardware stuff, I can totally do anything hardware, and it's like I'm working with another PhD, and it's like, oh man, it's like software stuff. It's like dumb.
Nah, it's easy. The robot just goes where you tell it to go.
So here, like this is like mostly like the actual object detection is just like dumb, right? It's not the connect. It's not like actually doing ML.
It doesn't need to, right? Because it has a person in that system that connects those dots for perceived intelligence and perceived connection. So a lot of people that experience these, they think that the robot's feeling something, and the robot is just reflecting the robot's a mirror, and it's reflecting their connection back and forth. But because there's that fluid, continuous interaction in this interface, that it's exactly how you would interact with an animal that you didn't know what it was. Like you see something on the ground, you poke it with a stick, and it jumps, and it's like, oh, it's a frog. Okay, now I know a little bit more about that creature. And that's what these software interfaces do. It lets you kind of poke and prod at the robot and see how it responds, and you kind of respond in unintentionally in kind. Now that's all my secrets. Poke it with a stick. Thanks guys for coming. I hope you enjoyed it. And if I see you tonight, it'll be a lot of the same content, but more of a cultural focus. So a lot of the same visuals, but different words. But yeah, I look forward to seeing what you guys put out in Ken's lab as well. I know you guys have a lot of deadlines coming up. But yeah, thanks for your time.